Okay, right, let's make a start. Yeah, so just to say very briefly again, this is a bridge building workshop for the Korean Regional Contest of the IBBC. I'm Mark Ancliffe. I work at Trinity Consulting, and I'm the coordinator for the Korean region. And yeah, so the purpose of this presentation that I'm going to do is to teach you the basics about bridges and the physics behind bridges. And then we'll talk a little bit about the specific bridges that you have to design for the contest, and then look at the contest rules and how it's gonna happen on the day. Okay. So I'll start now. If you have any questions or anything, you can't hear me or something, please do shout out or write a message, and I'll respond to them when is appropriate. Okay. So here I've just chosen 4 pictures of bridges. Um, just to illustrate the different ways that bridges can be built. And hopefully, I'm hoping that you'll recognize some of these bridges. So these are all bridges which are on the Han River in Seoul, and they nicely illustrate some of the different design principles of Korean bridges. Okay, so see how many of them you can recognize, and then I'll tell you what they are in a second. Okay. So first of all, this one on the top left. This is Bampo Bridge. And this is an example of a truss bridge, which we'll talk about in the next slide. Then the one next to it is the newest bridge in these pictures. This is the World Cup Bridge, which was only opened a few years ago. And you can see it has a very different design. And then the one on the bottom left, this is Wonhyo Bridge, which is an example of just a simple arch bridge. And finally, on the bottom right, this is Hangang Daegyo. Okay, so yeah, so the 4 pictures of bridges nicely illustrate the different ways that you can design bridges. Okay, and these are models which basically show the same kind of ideas. So one of the earliest and simplest kind of bridge is called an arch bridge. The arch refers to this curved undersection of the bridge here, and this convex shape is very good at distributing the forces. So if you have any load in the center of the bridge, it's a very effective way to transfer that load, that force, down to the support structures on either side of the bridge. Okay. Next on, let's go down to the truss bridge next. Okay. A truss bridge is just any bridge which is made out of triangular structures. Triangles appear in lots of bridge designs just because a triangle is a rigid shape. If you make a shape with, say, 4 sides, like a square or something, then the joints are susceptible to shear forces. You can push them. And the joints, even though the lengths of the different members don't change, the shape can change. Okay, so it's not stable. Whereas triangles, they are stable. As long as the members, the parts that connect the 3 sides of the triangle, are strong, the triangle shape cannot change. Okay, and that's the basis behind a truss bridge. Okay. Then on the right-hand side, you have 2 similar designs, the suspension bridge and the cable stay bridge. So both of these bridges use the idea of a tower to take the main load of the bridge, and then attached to this tower you have cables. The difference is in a cable stay bridge, you have cables, only one type of cable directly connected to the tower. Okay, so if we go back, the World Cup bridge on the top right here, this is an example of a cable stayed bridge. Okay, the cables are directly connected to the tower. Whereas on the suspension bridge, you have a main cable which links the 2 towers on either side, and then you have sub cables coming off that which support the actual bridge. Okay. So those are the different kinds of bridge structures, and you can see them all here, really. So you have something like a suspension bridge in the center of Bampo Daegyo here. And of course, you have truss structures around the outside. I already said this is a cable stay bridge, and Wonyo Daegyo is a nice illustration of a arch bridge. Okay, so when you're designing bridges, the most important thing is that they don't break. And in order to make sure they don't break, you need to consider what are the forces on the bridge. So how strong are each of the different parts of the bridge, and how large is the force that they have to sustain. So the simplest model of a bridge is divided into what are known as nodes and members. So the nodes refer to the vertices, so like the points where two structures meet. If I make a very simple model of a bridge over here. And the members refer to the edges, so the parts that join these. So these would be the members here, like this. Okay, and then joining them up, we get a very simple here. This would be a truss bridge made up of triangles. Okay, so if we assume that this is like these members are one-dimensional, so they're really just rigid sticks, which isn't true, but is a simple approximation, then there's only two kinds of force that each member can have, and these are forces either compression or tension. Okay, so a compressive force is a force where the two edges of the member are trying to be pushed together, squishing like this, and a tensile force or tension is where the two edges are trying to be pulled apart from each other, like this. Okay, and it's for some reason usual to color compression in red and tension in blue. Okay, I don't know why, but that seems to be the convention. So going back to these bridges here, I have done that coloring. So for example, in an arch bridge, the arch is under compression, and it's the compression that transfers the weight, the load on the bridge to the support structures. In the suspension bridges, so suspension and cable stay bridges, the main towers are under compression. They take the weight of the bridge, and then the cable parts are under tension. Okay, so a cable, in fact, refers to a structure which is, you know, like a piece of string. So under compression, it just collapses, but under tension, it can be quite strong. Okay, so therefore, the cable parts of these bridges are necessarily in tension. Right? If it was in compression, they would just collapse. And then on a truss bridge, you can have different members in tension and in compression. Okay, so I want to start building a physical model of what a bridge looks like, and we need to make some approximations. So we've already said that we're going to assume these members are one-dimensional, so we're not going to look at like twisting forces and this kind of stuff, but only compression and tension. Again, we're going to make it simple by assuming they're incompressible, so you can't squash them. The force doesn't change the length of these members, which, you know, for these wooden bridges we're building is a good assumption. You know, not exactly true, but close enough. And then the second point here, I already said, if you make your bridge out of triangle shapes, then that means those triangle shapes cannot change. So as long as the members are incompressible, then, and you make the bridge out of triangles, the shape of the bridge is fixed. Okay, until something catastrophic happens and a member breaks or so on. Okay, so now we want to look at how can you start calculating forces on a bridge. And here we're going to use Newton's second law of motion, and in fact, we need a simpler version of the second law of motion. Any net force on an object will cause that object to accelerate. Okay. And in particular, you don't want your bridge to move, right? Bridge needs to be a stationary, stable structure. So that means if we look at the forces on any member or any node on the bridge, then those forces must add up to 0. Because if they weren't 0, that would be a sign that that member or that node is going to move, which is what we don't want. Okay. And okay, so yeah, so let me quickly draw an example of what I might mean by that. So if I suppose that I have like a member here, which is, sorry, I have a node there which is attached to 3 members like this. And suppose that I know that this member at the top is in compression. That means that it's applying an outward force on this node like this. Okay. So now, if that was the only force on this node, then this node would start to accelerate downwards, which again means the bridge is collapsing. So that's bad. So in order for that not to be the case, these 2 other nodes here must have an upwards component. Okay, so that means that the force from this node must be pointing up to balance it. Okay, and again, if those were the only 2 forces on the bridge, then add them together. At the moment, it looks like this. We've got these 2 forces, and that would give us a net acceleration in this direction. Right, and again, that's not good. So to balance that, we need to have a force. Sorry, the final force on this member pointing on the node like that. So then we get 3 forces like this, and then if we add them all up, calculate the net force on the node, like this, you see that it adds up to 0. So these 3 vector forces, I call them like F1, F2, and F3. If I add these 3 forces together, I get 0, and that's good. Okay, so that implies that this node is stable, it's not going to move. Okay, so that's what you need. And in particular, what that shows you here is that if the first member is under tension, sorry, is under compression, as I've drawn it, right? Compression would mean that it's pushing the node away from it. Then the other members must also be in compression in this particular case. So here I have 3 members which must all be in compression in order for the bridge to be stable. Okay, so that's an idea, but we could actually go further than this and make this idea quantitative. Okay, so there's a quick quiz here. So here below you can see 2 cases similar to what I drew, so a node connected by 3 members. And the only difference between case A and case B is the angle between the members. So case A has a much wider angle here. Case B has a narrower angle there. And suppose that I apply a downward force. I know that the lower member has a 10 Newton force pulling the member down, sorry, pulling the node down here. Then what should the forces be on the non-vertical members? So in this case, the non-vertical members are these ones, right? Okay, and I break this down into 2 questions. Firstly, are they in tension or compression? And then secondly, comparing A and B, which one will have the greater force in the members? Okay, so I'll give you a second to think about that, or maybe 20, 30 seconds. Do try and work it out. If you want to say, you can say. If you don't want to, you can just wait and I'll tell you the answer. Okay, so let me get some answers then. So number 1, are the non-vertical members, are they going to be in tension or in compression? Okay, so these, it actually turns out these are going to be in tension. Okay, and the reason is similar to the last slide. In the last slide, we found if one of the members was in compression, then they should all be in compression. And it works the same with tension. So the fact that this member is pulling the node down means that the remaining two members must pull the node up. So that means we must have forces which look like this, which means that they are all in tension. Okay. So the first question, the answer is tension. And then which of A and B has the greater force? So here the answer is A has a greater force. Okay. And again, what's the reason for that? Well, here the downward force is 10 newtons, and because of the symmetry of the situation here, that means that these two members must provide an upward force of 5 newtons each to balance that. But then if you imagine, what does this upward force of 5 newtons look like? Because of the angle of the members, that corresponds to a much greater force in the case A. Like, just look at the length of the arrow in case A, right? It's much longer, that means a much greater force than in case B. Okay, so we can quantitatively analyze the forces using this idea. Okay, and why is this important? Well, as we'll go on to talk about when we start making our bridges out of these wooden sticks, they have maximum forces they can sustain. So whether they're in tension or compression, there's a critical force beyond which these sticks are going to break. That means you need to design your bridge to keep these forces as small as possible. So in this particular example here, if it's possible, design B is better than design A, because design B will lead to less force on these members, and that means less chance of them breaking. Okay, so there's one more exercise here, again, with a similar situation, but now I want an actual numerical answer. So I've taken the case where I tell you now what the angle is. And the angle of these members is 45 degrees to the horizontal. And now you can calculate exactly what should be the force on each of, what should be the force on each of these members. Okay, so again, I'll give you 30 seconds or so to calculate it, and I'll show you the answer. Okay, so somebody did write an answer in chat, 5 newtons. So 5 newtons is not the total force. 5 newtons is actually the component of the force in the vertical direction. So same as in the last case, in order to counteract the downward force, you need to have 5 newtons in the vertical component of each of these. But now we can just draw a diagram to work out what the total force. So the total force is this red arrow here. And because we know it's 45 degrees, this is the total force. And then the vertical component of the force is 5 newtons. Because it's 45 degrees, that means the horizontal component of the force must also be 5 newtons. This is a right angle, and now you can use Pythagoras' theorem to get that the total force here is like 5 squared plus 5 squared square root. So that gives you root 50, which comes out as about 7.07 newtons. Okay, so this is just to show you like how you can, using geometry, trigonometry, and this notion of balanced forces, you can calculate the exact force on every member or node in your bridge. Okay. So you might be thinking, well, that's a lot of work. Like a bridge from this contest would look something like this. This is one I built to illustrate it. So you can see it's got loads of members, loads of nodes, and if you have to do this calculation yourself, that's going to give you a real headache. So, I'm not suggesting you do that. But what I think might be a good idea to do is you can find software online that will do this for you. Okay, let me come back to that. Okay. You can find software online that will do that for you, and an example of that software is here. This is called a free trust calculator. I'll put this link into chat as well in case anybody wants to copy it. Although it looks like I can't do this. Okay, well, I'll do it this way. Okay, I know there are lots of websites that allow you to do this, but this is one that I use, and I'll just quickly show you how it works. Okay, so if you make an account on this website, then you get a page which looks like this. Welcome, Mark. And the thing that you want to use here is this trust frame calculator. If it loads. Yeah, so then you'll see in a minute. So here we can build a model. It has nodes, members, and supports. Okay, so let's quickly build our model. So I'm going to make a simple trust bridge just to show you. So I'm going to have the first node at the origin. So you can see it's appeared in the center here. That's going to be one of my supports. And then I'm going to make a new node displaced from that. So let's say displaced by 20. So it says meters here, but like the units are not that important. Okay, and then to make this a truss bridge, I want one more in the center, so that will be at 10. And then I'm going to put some nodes higher up. So let's displace those by, let's say, 10 in the y direction, and those will be in between. So those will be at 5 and 15. Okay, so hopefully you can see here now I've created these 5 nodes which have numbers, and now we can join them up with members. So to do this, a member, you just say which node it connects. So my first member is going to connect 1 and 3. Okay, type, just leave it as normal. Then 3 and 2. Then 1 and 4. Then 3 and 4. Then 3 and 5. 2 and 5. 4 and 5. Okay, so that gives me a simple truss bridge. So I want to calculate the forces. Well, at the moment, there's no forces because we're assuming that these members are massless, right? Again, for our bridge in our contest, that's a good approximation because these wooden sticks, as you probably know if you've got the kit, they are very, very light. So the bridge weight is maximum 25 grams, but they will hold weights of 25 kilograms, right? So like 1,000 times more. So the weight of the bridge itself is basically 0 in our case. So we need to put a weight on the bridge, and then we're going to use that with this point load thing here. So in this case, I'm going to put a load on the central node, so that's number 3. And I'm just going to have it going straight down. So x magnitude is 0, y magnitude is, let's say, minus 10. And again, the units are not particularly important. So you can see here I've got a force of 10 pulling down. So this would be as if I put a heavy weight in the center of my bridge. So now finally I need to say where the supports of this bridge should be, and they want to be at nodes 1 and 2. So node 1 is going to have a support, and I will make it this one, yeah, fixed support. And node 2 should also have a support, which I will make into this horizontal roller. Okay, so this horizontal roller just means that it can move side to side. So the support is only offering vertical support. It's not offering horizontal support, which is what will be the case in the contest. Okay, so now you can see I've got fixed support at number 1 and rolling support at number 2. And that should be everything. So I've put the nodes, I've said how they're connected by members, I've put the load in the center, and I've put the supports at either side. So now we can do the main point of this, which is to calculate all the forces. So now this software will calculate all the forces for you. If I click up here, solve. Okay. So it's completed the solution. And now on the left-hand side menu, you have lots of things you could look at. So most of them you have to pay to look at, but fortunately, we don't need to pay. So the only thing we're interested in is these axial forces. Axial forces are tension and compression. And if we click on them, you'll now see that some numbers magically appear. Can I zoom in a bit? Zooming in doesn't change the font size, unfortunately. Okay. So I'm not sure if that's big enough to read on your screen, but what this is showing is that the 4 inner members here are colored blue. That means they are under tension. The outer members are colored red. That means they're under compression. And the forces, we have 2.5, let's say, newtons. As I said, the units doesn't matter. 2.5 newtons on these horizontal members. And then the diagonal members all have a force of 5.59 newtons. Okay. And the top member has a force of 5 newtons of compression. Okay. So that means it's actually quite a nicely designed bridge if this was, the correct load and parameters for the contest, which is not. The reason it's nicely designed is because all of these numbers are about the same, right? If you had one where the number was much, much bigger than the others, then that means that you've got a badly designed bridge. In fact, maybe I can quickly illustrate that. So one way I could make this design worse is if I take these vertical nodes, sorry, these upper nodes here, 4 and 5, and I just shift them down. So let's say I'll move it down. Instead of being at 10, I'm going to move it down to 3, like this. Okay, and I'm going to take node 5 as well, and I'm going to move it down to 3. Okay, and let's see what that does to the forces. Okay, so you can now see that these forces, even though the load is the same, the forces have got much bigger. And in particular, this upper member here now has a force of 16 newtons, okay, which is more than 3 times what it was before. Okay, so this, there we go. So this would be an example of where your bridge design needs some reinforcement or some modification. Okay, so we have much, much bigger forces here. So one of the reasons that this contest is interesting, though, is I said the previous design is better, and it certainly is better in terms of giving you smaller forces on the bridge, but it would use more wood, right? So because you're making it higher, that obviously uses more wooden sticks to make the bigger bridge. And in the contest, your score is the amount of weight, the amount of load that the bridge can hold divided by the weight of the bridge itself. So the more wood you use to make your bridge, the more load your bridge has to carry. So that's what makes it interesting. So there's this competition. If you make, for example, in this case, if you make the bridge taller, that reduces the forces, but it also means you're using more wood, which will reduce your overall score. So which is better? And you have to find the right point of balance to make a good bridge. Okay, so I think I'll stop there. But just to say that software like this, it's called a truss calculator. Truss is those triangle parts that you calculate the forces on. They are useful to think about how to design the bridge and to help you work out what parts of the bridge might need strengthening or redesigning. Okay. Yes. Yeah. Okay. Right. So now we can go back to the presentation, and I'll go back to these slides that we missed. Okay. So this slide I've basically already said. Um, your contest bridge probably shouldn't look like exactly like those bridges that I showed you in the first slide, the real bridges. And the reason for that is the kind of load that they need to carry. Because those bridges, like, Bampo Degyo, this kind of thing, the vast majority of the weight is the weight of the bridge itself, right? So the bridge weighs many, many thousands of tons, and a single car or whatever crossing over that bridge weighs just a few tons. So the main force that the bridge has to sustain is the weight of itself, right? But the contest bridges is completely the opposite. In the contest bridge, the weight of the bridge is near to zero, and it has to sustain, it has to carry a point load, so a very large force on a single point on the bridge, or as close to a single point as you can get. Right? And that naturally means that the design of the bridge shouldn't be the same, because your whole focus should be, how do I distribute this force, which I apply here, singly here? How do I distribute this force down either side, down onto the supports? That's all that matters. Right? The weight of the bridge itself is negligible. Yeah, so we can consider the load as a point load, as I did in that simulation. Okay, so there's another exercise here, which is basically what we did with the simulation. We put, support structures on either side, a force in the center, and you worked out, or the computer worked out, which parts of the bridge should be in compression or tension. So, yeah, I think in the interest of time, I'll just skip this quickly, but it is useful exercise to look at this and see if you can work out which parts should be in tension and compression and why. Okay. There's only one way to balance the forces. Okay. Right. So that's sort of the end of the introduction to the physics of bridges and so on. So the last part, well, the second part of the presentation is looking at how do we actually build bridges for this contest. So on our YouTube channel, there is a video of last year's contest, which will give you a good idea of what happens. So we take your bridges, we put them suspended across this 30-centimeter span, and then we load them with weights until they fail, until they break. And there's two main ways in which they can break. You can have what's called a member failure or a joint failure. So a member failure is simply when the wooden stick snaps. Okay. And the joint failure is when a part where two sticks meet and you've glued them together, and that gluing joint was not strong enough, and that's come apart. Okay, so that's a joint failure, that's a member failure. And of the bridges from last year, we did see both kinds of failure. It's quite hard to tell which is first, because often what happens is one thing breaks, and that means that everything else breaks. Because, of course, once one member breaks, then the forces that this member was carrying have to be distributed throughout the rest of the bridge, and that causes other parts to break as well. So you get this sort of chain reaction. But we did see both member failure and joint failure in the bridges that were submitted last year. Okay, so some points to consider for each of these breaks, for each of these failures. So member failure. So member failure happens when the force on these sticks is too large. Okay, and if we consider just those two forces, compression and tension, then these basswood sticks are much stronger in compression much stronger in tension than in compression. Okay, so if you have some of these sticks and you have a bit left over, then you can actually do a simple exercise to show this to yourself. I just stop sharing for a second. Yeah. So, okay. Here's an example of a piece of a stick. So tension would be holding the two ends and trying to pull it apart. And I can use my whole strength, and I can't do it, right? So they're very strong in tension. You might be stronger than me. Maybe you can do it, but they're very strong in tension, right? Whereas compression, pushing them together, I'm not sure if you saw that, but it did break, right? So they're much weaker under compressive forces. Okay, so that's the first thing to consider. So the parts of your bridge which are under compression are the parts which need strengthening. Another thing to consider is for compressive forces, the length of the member matters. For tensile forces, so for tension, the forces try to keep the member straight, right? So the member will stay straight under tension. But under compression, the member will start to bend, which is something that we didn't consider in our simple model. But again, it's a very easy test. Take a short piece of wood and try and bend it. It's hard. It doesn't want to bend, right? Whereas a long piece of wood will bend very easily. And this means that the longer the member is, the weaker it will be under compression because of this bending influence. And again, if I take a short piece of wood like this, I can push as hard as I can, and I won't be able to break it. Okay, so yeah, so that's an important point. So that the parts of the bridge under compression are where you need to think about strengthening. Tension, the basswood stick, like one stick will hold, I don't know, 20, 30 kilograms, or the equivalent of 300 newtons of force. Okay, so that's member failure. Joint failure, this is where the glue basically fails. Okay, and on the next slide, we'll talk about this in detail, but the basic idea is the strength of that bond depends upon how big the surface is. So where these two sticks meet, they meet with a certain area, cross-sectional area, which are stuck. The bigger this area is, the stronger the joint will be. Okay. And there are two main ways of joining, what's known as a lap joint and a butt joint. And on the next slide, I explain what those are. Okay, so a lap joint is where two sticks overlap each other. That's why it's called a lap joint. So in other words, they cross like this, and you glue the section where they cross. Okay. A butt joint is where they meet end on like this, and you glue the ends together, or at least you glue one end together like this. Okay. So I find the easiest way to draw it, if that's not quite clear, is something like this. So in a lap joint, suppose I have two members just coming straight onto each other like this. In a lap joint, I'll put one member over the other like this, and then I'll glue this surface here. In a butt joint, I'll have both ends touching like this, and I'll glue the ends like this. Okay, so what are the advantages and disadvantages of these kinds of joints? Well, a lap joint, you can make the surface area much bigger, right? If I want to make the surface area bigger, I can just make the overlap bigger, right? And that means that makes the joint stronger. So lap joints you can generally make stronger than butt joints because the glued surface is larger. Okay. Butt joints, though, have an advantage in compression, which is, if I again draw this a bit bigger this time. Okay, so imagine that I have these two members which are in compression. That means they're pushing against each other like this. Then in this case, as long as I've made the joint, I've cut these pieces of wood well so they're not sloped and everything, then in fact the glue is not that important because the force will be transmitted straight through the wood into the other piece of wood. So if the members are in compression and I have a butt joint and I cut that butt joint well, then the strength of the glue becomes less important. So that's the diagram there is if the case where two members meet. If you have three members meeting, say like we drew before, then you can have a similar thing, but you just need to be more careful how you cut them. Here, the correct thing to do would be to cut them like this, so little arrows on each side. And again, if these were on compression, then the force would be transmitted through the wood, and the glue would not have to maintain a large force at all. Okay, so the glue becomes less important. Okay, so what that means, end of the story, if you're joining a member which is in tension, then a lap joint is a good choice because you get a large surface area, strong joint. If you're joining two members in compression, so they're pushing against each other, then a butt joint might be better as long as you are careful how you cut it. Why do I say careful how you cut it? Well, say in this case you cut it like this, then that's bad, right? Because now the glue has to stop the members sliding off each other. Okay, so we've looked at member failure and we've looked at joint failure in these bridges. Okay, okay, so I think this is just what I drew on the last slide. Okay, so now I want to talk about strengthening members. So in your basic bridge, a member is just one stick, right? But suppose that from your calculations or whatever, you think a member needs strengthening. So that could be a long member which is under compression, or it could be a member which just carries a large amount of force. Then how can you strengthen it? Well, the simplest thing to do is just to join two sticks together, right? Two sticks is twice as strong. Sorry. Two sticks is twice as strong as one stick. So if I can draw have two sticks like this, and I glue them together, then I've doubled the strength. In fact, I've more than doubled the strength because it's much more resilient to bending as well. Okay, so that's one way to strengthen a member which has to carry a large force or you're worried about. An even better way, but which again comes at a cost of weight, is instead of having a single member, make a truss. So say this is a member I want to reinforce, then I could put another one parallel to it and then put pieces across like this to make a truss. Okay, and again that will be much, much stronger, but it will use more wood, which is the downside. Okay, so if you can look, again, let me briefly pause the sharing the screen. If you look at this bridge I've designed here, this is a really simple design. You know, I didn't spend much time designing this. It's just an arch bridge, so you can see an arch at the bottom, and as we saw, the arch has to carry a large amount of compressive force, which is, you know, what these sticks are weak against, and therefore I just basically turn the arch into a truss. So I put these extra members around it and I put truss elements between them to make triangles. And that's basically the whole design of the bridge, right? It's very simple, and I've just strengthened this member, which is going to be under a large amount of compressive force. I'm not saying this is a great design for a bridge, by the way. You know, I just threw it together very quickly just to illustrate what a contest bridge, the properties a contest bridge needs to have. Okay, so we're nearly at the end now. Yeah, types of glue. So in the kit, we provide this glue on the left. This is an all-purpose super glue, as it's called. And again, it has some advantages and disadvantages. The main reason we give this glue in the kit is it's easy to make reasonably strong joints with this glue. It dries very quickly. So if you just hold these two sticks together for about a minute, just with the force of your hand, then okay, we've got one more person coming in. Okay, just with the force of your hand, then that will be like solidly glued just within a minute. Okay, so it's very quick, and it gives quite reliable bonds. Okay, so one of the cons of this is that it's not the strongest glue you can get. Okay. So an example of a stronger glue is something called carpenter's glue here. So this is a glue specifically designed for gluing wooden pieces together. And in terms of the strength of the bond compared to the amount of glue you use, this glue is stronger. Okay. But the reason we don't provide it in the kits is that it's much, much harder to work with. So it takes a long time to dry. So rather than just having to hold these sticks together for a minute, you have to hold them together for a day in order to get a strong, solid bond. And that means it's much more easy to make mistakes. Like, you know, if during that drying time, especially the first hour, you shift the bridge a bit and it moves the two sticks a little bit, then your bond is ruined. Okay, And it just, even though it should in principle be stronger, it ends up being much weaker because it's much harder to hold securely while it dries. Yeah, and I did some experiments with these different kinds of glue, and I basically concluded that generally the all-purpose glue is actually safer. It doesn't always give stronger bonds, but it gives you a much better chance of not having weak bonds. Okay. That said, in the regulations, which we'll come to next, you can use any kind of glue. So if you want to go and buy a different kind of glue and use that, that's entirely within the rules of the contest. You don't have to use the glue provided. Okay. So this is now the final part of the presentation. And here I'm just going to go through the regulations for the contest. So these are on the website. And okay. Yeah, okay, yeah. So these are on the website. And just a few things I want to point out. Okay, so the first thing is you must use the sticks from the kit. You're not allowed to use any other kind of wood because that's definitely a way to get an advantage. But you can use any kind of glue that you want. You can cut the sticks however you want, but you're not allowed to use any other materials. And in particular, you're not allowed to coat the sticks with anything like epoxy or whatever to make it stronger. Okay. Okay. So the construction parts you need to pay attention to, because the first thing we will do on the contest day is to check that the bridge meets all of these regulations. And if it doesn't, then we will still test your bridge, just it's sad otherwise, but you will not get an official ranking in the contest if your bridge doesn't match these parameters. Okay. So firstly, weight. So no more than 25 grams. So if you weigh all of the sticks that came in the kit, it's much more than 25 grams. So, we give you extra so you can break things and so on. But the bridge itself must be less than 25 grams. Part B here is all about the dimensions of the bridge, the width, the length, and the height. The new part for this year, which I'll spend a bit of time concentrating on, is this part below the support surfaces. So the support surfaces are it's going to be wooden, and it's going to be a 90-degree angle here at the edge of the support. Let me draw. Okay. Yeah, so here there's a 90-degree overhang here, and your bridge, and this is new this year, your bridge must come down and make contact with this vertical surface here. Okay, and in between the two vertical surfaces, you must have some kind of arch structure. Okay, that's point C here. Bridge must contain an arch type structure. Okay. However, the amount it should go below is very small. It must go no more than 10 millimeters. So that's just 1 centimeter below these support structures. I don't know if you can see it on the bridge I built, but if I hold it up close to the camera, you can see I've made a sort of right angle shape at the bottom of the bridge, and that's designed so that it will sit on the support structure like this, just slightly hang down. Okay. Again, you can also see the arch structure here. So the arch doesn't have to be curved. I made mine curved, but if you want, it says you can just use an A-frame. An A-frame is just a structure which looks like this. Right? As the name suggests, looks like the letter A. So 2 sticks there. This will be where the support is, like this. Okay, and then joined together in the middle to make this A shape. So if you don't want to go through the hassle of curving the wood, you can just make it with straight pieces here. If you want to know how to curve the wood, there are instructions in the kit. Basically, you just have to soak the wood in water overnight or for about 24 hours. After that, it becomes very soft and pliable. And you can basically then bend it into whatever shape you want, hold it in place with tape or pins or whatever, and then let it completely dry in the bent shape. And then once it's dried, it will keep that shape. It will stay bent. Okay. So, but like I say, that's not necessary. Okay, yeah, so yeah, please be careful to make sure that your bridge is within these parameters. Last year we had a couple of bridges that weren't, and as I said, it's a shame because they are disqualified from the competition. Although we will still test them, but you won't get a score. Okay, so the next one is loading plane. Loading plane is important because this is where the weight is going to be attached to the bridge. Um, and I think this is best illustrated in the template, which again is provided with the kit. That's here. Okay, so if you order the kit, you should get a template which looks like this. This is to scale, so the support surfaces have exactly 30 centimeters apart and a 1 centimeter overhang here. So this graphed area is the area within which your bridge must fit. And the place where the point load will be applied is this loading position 1, loading position 2. So on the day of the contest, we choose one of these two positions. It will be chosen at random by me, the judge. And all of the bridges will be tested either at position 1 or position 2. So this is just so you can't design your bridge with just a single point. It has to have at least 2 points at which it can be loaded. Okay, and the height is flexible, and that's what these vertical lines are on the template. The height is flexible, but the horizontal displacement from the center, so like this position, those are fixed by the rules, and it's 2 centimeters, 4 centimeters either side of center. Okay. So whatever you do, you need to design your bridge. Say if I'm going to say that the top of my bridge is going to be here, I need to design my bridge so that this part is very strong. Okay, this part is strong, and also there's a way of transferring the force from this part down to the support structures. Let's go back here. Okay, so that's loading points. Okay, so how does the loading take place? There is a metal plate which measures 4 by 4 centimeters. That's shown in the picture here. And that will be placed on top of the bridge. Okay, I don't have it with me now. Again, maybe I'll cancel it and show you. Again, this is something important when you design the bridge. Okay, so in my bridge here, you can see I've reinforced the top with these pieces here, and the first loading plane would be placing that metal piece here between these two wooden pieces, and the second one will be placing it here between these two wooden pieces. Okay, so even whichever point is chosen in the contest, either it will be placed here or it will be placed there, like that. Okay, okay, and it has to be designed so that this plate 4 by 4 centimeters will fit on top of the bridge, and there should be a hole in the center where the load will be applied. So if we look at the picture on the regulations, here we go. Yeah, so this is the 4 by 4 centimeter plate, and in the center of this plate there is a metal rod, and this metal rod hangs down through the bridge, and then we load the weights at the bottom. Okay, again, if you watch the contest video from last year, that will give you some good idea about how the testing is done. So on the day, we do give you the option of testing your own bridge with supervision. So you can put the weights on yourself, or you can let the judges do it. Okay, so yeah, finally testing. Okay, so how do we test them? We put them on the support structures. Well, first of all, we check that they're within the regulations, size and everything. Put them on the support structures, attach the loading plate and the rod, and then we will start increasing the load on the bridge. So we do this with weights. Between 0 and 10 kilograms, we go up in units of 1 kilogram. So we'll test 1 kilogram, 2, 3, 4, 5, 6, 7, 8, 9, 10. Above 10 kilograms, we go up in units of 2 kilograms. So we'll go 10, 12, 14, 16, 18, 20. And the maximum is 50. So last time we didn't have any bridges which got up to 50. I think the highest was about 36 or something like that kilograms. which is still a lot of weight. But yeah, if they sustain 50, then that's the maximum. We don't go any higher. Okay, and E is very important. E is how we decide who wins the competition. So we convert the mass that was put on the bridge into grams. So let's say if it was 20 kilograms, that would be 20,000 grams. And we divide that by the mass of the bridge in grams, which is something less than 25. And that will give you a score. Okay, so last year, I think the winning score in the Korean contest was about 2,000. Okay. I think it was maybe 1,800, slightly less than 2,000. The highest score I've ever seen in the international contest was slightly over 3,000, which is quite amazing, right? This means that this bridge can hold 3,000 times its own weight, which is a very impressive result. Okay, but that's it. Okay, and then we test all the bridges like this. We define like first, second, third, fourth place, and so on. And the top two places. The top two places will then be eligible to join the international competition, which it will be held in America in April. Okay. So this is the final slide. Well done for reaching this far. So this is just contest information. So it will be held 15th of February, that's a Saturday, 2 p.m. In Daegu. If you can't make it to Daegu, you can send your bridges in the post. If you do, just make sure you wrap them very carefully. It's your responsibility to make sure they arrive not broken. After that, we'll do everything we can to look after them for you. And if you can't make it to Daegu on the contest date, the contest is recorded, so you will be able to watch a recording of it later on, as well as seeing your own score. So I guess most of you already registered. If you haven't, then the link to register is here. You can also find it on our website. If you are sending a bridge by mail, then it must get to us by the day before. That's Friday the 14th. And that's everything, I think. So I don't think I've given you my contact details. Yeah, okay. But my contact details are on this website. So if you go to this link here, you can find the way to contact me. If you have any questions, that's the best thing to do. And that's it. So I hope this sounds interesting to you, and I hope we'll have a good contest. And I look forward to meeting you, or at least seeing your bridges on February the 15th.